Okay, so let's get going. So yesterday I just gave you a glimpse of some of the ingredients in numerical relativity. My goal is not so much to give you a complete description, but give you enough that if you have a particular interest to get in, you realize or you get enough tools to get yourself started. There are plenty of good resources out there. There are several books that you can follow. The notes I had as a pre-reading material has in the first page. This is a kind of a lecture notes that Sebastiano Berluzzi wrote a few years ago that actually is quite good to get yourself started. The books that are listed there are also quite reasonable. But it's a field that is kind of changing and evolving rapidly in front of our eyes. So I always tell anyone, be suspicious of any result that was done with a code working at the bleeding edge if it hasn't been kind of reproduced later when you have better resources. And so the same thing, so there are sometimes, I'll tell you one story. So yesterday we were discussing this generalized harmonic. When Franz got his first binary black hole collision, he had to use a very particular choice for these source functions for the gauge. And people for a number of years kept repeating, if you're going to use harmonic, you have to use the sources that Franz used. And that was because Franz was squeezing the very last thing that he could get out of the available resources. But within a year, people were colliding binary black holes with the harmonic formulation without having to use any source whatsoever. It was just a testament that, well, when you're at the bleeding edge, well, sometimes you have to make choices that end up being superfluous once you have the ability to look at the system with a more powerful approach. So always be careful with that. So we're gonna move today. I'm gonna discuss some other things related to what and how you try and make up something like this. I mean, to obtain a gravitational wave, the theme of the school is gravitational waves in particular. And so I'm gonna kind of focus now in that direction. We're going to try and discuss objects that actually produce these, and then the kind of things that we need to worry about as we move along. So we're going to discuss perhaps a little bit of what happens when we have black holes, neutron stars, and then open the door. Question whether the objects that we know and love, in particular black holes, the ones that we seem to be seeing the most, whether they are described in the way we want, and the assumption that they are stable, whether that is, if we push that to the extreme, where we might be missing something, and that's important. We want to understand what can they do when they interact. What is it we have to do when and how. Kind of contrast numbers versus understanding with some examples. And eventually we'll also, maybe tomorrow, we'll describe kind of what rules them given what we see in the signal. And so let me just perhaps motivate with some examples. So as Patricia described, the type of the approach that you can use earlier on is post-Newtonian, post-Minkowskian now, and a few other options. Then afterwards, if you wait long enough, there is a ring down. We understand, or we think we understand this, in terms of the assumption of a black hole that has been formed that is not changing. We can assume the black hole is a background, and we have test fields on top of it. And numerical relativity is there to fill in the gaps, the merger. And of course, as numerical relativity gets results, people get clever, and they try to understand where there are some effective ways, not only to encode the numbers more efficiently, but perhaps if we understand the behavior of the system at a deeper level, we might find that there are shortcuts that one can use here to complete the waveform. In particular, something that people are doing nowadays, which is in a very exciting way, they're using things that are called self-force approximation. Neil described Embreeze a little bit today, which is a case where you can imagine a binary where the mass ratio is so large that the smaller mass is considered as a perturbation in the background of the larger object. And then by accounting in a different type of perturbation for the back reaction of that object, you can get what the waveform would be all the way to the merger of two objects and afterwards. But of course, that's in the extreme mass ratio regime. But people have found out that as they take that mass ratio and they extrapolate from there to the more or less comparable mass ratio case, and they go through some particular mapping of the, say, masses and parameters of the system, you get a pretty good approximation of what happens throughout. So in principle, in some regime, you might even dispense altogether with the numerical relativity part in the middle. But of course, you wouldn't know that you could do that unless you actually solve the problem and contrast and see that indeed you're getting a reasonably good approximation. On the flip side, however, the detectors are getting better, and the accuracy of the gravitational waves you're producing, the requirements keep going up. So I'll give you one example today. The current detectors have gotten better, and there's a very high chance that as you wait after the merger, more than one mode will be extracted. If you do extract more than one mode, you can do an amazing test of general relativity, because if it is true that the system at the end relaxes to a curved black hole, perturbations of curved black hole tell us that there are this thing called quasi-normal modes, exponentially decaying oscillations, that are completely determined by the mass and spin of the black hole. So if you measure in one mode, you have two numbers, the decay and the frequency. With that, you can extract just by, you can ignore everything before, you extract the decay and the oscillation frequency. That tells you what the mass and spin is if you assume it's curved. But if you have a second mode, now you have two ways of getting the same numbers, and if those numbers agree, then you're golden. However, when do you start this? I mean, this is the assumption here is you are sufficiently late in the system that the system is now behaving linearly. But we have a set of equations that are truly nonlinear, or they are nonlinear from in their characteristics. So at what point can you assume that it's safe to treat the system in a linear way? That's already a tension there. And as of this moment, there is quite a bit of back and forth between different groups claiming one thing or another. I mean, it seems like a silly academic discussion, but at the end of the day, there is a big prize if you can claim that there are two modes that you can measure. And of course, then, what is the right tool to understand when a nonlinear problem becomes linearly describable? It's not a trivial thing. So if I take my prop here, my bottle of water, and I'm shaking it, at some point I stop. And at some point, the system will become laminar. But when does it start? How strong can I make that assumption? What is the right tool or right quantity to measure to decide if that's the case? These are questions that are lingering out there. What else here? Okay, let's keep going. Wow. So now, remember, yesterday we described that Einstein's equations, and let's imagine, well, let's think of GAB, TAB, or maybe I'll throw in a pi here, has like two set of equations. There's this thing we call constraints, which has the Hamiltonian constraint and the momentum constraint. I think we call it pi. Remember, this was a scalar, this was a vector equation, and we have the evolution equations. These were two, if you want, set of 6 equations that were first ordered in time for the extrinsic curvature and the intrinsic metric. And this was one equation that was scalar, one equation that was a vectorial equation that did not involve second derivatives. So the second derivatives are here, and here at most they are first derivatives. And you have as an exercise to prove, as I said yesterday, that if you satisfy this initially and you evolve with this, then these things will be preserved, modulo what you do with boundaries. And this we'll discuss ever so slightly later. But now let's see, you're going to try and study a system. You would like to describe some initial time. Let's say you want to put two black holes physically corresponding to a situation that you might want to study. So how do we set this up? So we need to satisfy these equations. These equations are, well, let me just briefly rewrite them again. So if we're dealing with black holes, we don't have that. If we, on the other hand, we have neutron stars, we need to account for this. Let's take the simplest case. We don't have this. So now we have 4 equations, and we need to fix 12 unknowns. We need to specify what the gamma ij are and what the ki ij are. And so just as we would be doing if you want Maxwell's equations, so we have a box of E, we have a box of B, and if we're in the absence of sources is equal to 0, but we need to give dB equal to 0, dE equal to 0. So it is, if we look at the equations from this point of view, our data should be E, say on the time derivative of E, B on the time derivative of B, but they are not completely independent. They are constrained to satisfy this. So we can give a number. So here we would give, let's say, 6 pieces of information. If we're in time symmetry, we can set all the time derivatives to 0. But we have 6, but we have 2 equations, and we can only give 4. So here we have 12. We have 4 equations. We need to somehow give 8. So I'll tell you what typically is the first thing one can do. I'll mention some problems or some features. And I'll just briefly mention what people are doing in general. And I will anticipate this problem is not fully under control. Fully under control in the sense that you want a problem that will give you a way to define this initial data such that you know precisely the physics you want to see. And I'll tell you why it's not completely under control. Even though the solutions can be obtained, you don't have the complete physics specified in the sense that you would like a particular physical situation. So the one thing you could do is imagine we can do this choice. We're going to specify this intrinsic metric to be something, some scalar field to some given power. And here I'm going to put the flat metric, which I'm denoting by eta ij. So it's called the conformally flat choice. So that we can see here we're given 5 pieces of information. We have one that we want to determine, which is this 5. And then we can say, well, choose the kij's to be exactly equal to 0. So this at a moment of time symmetry, or we're choosing our initial slice so that it has no curvature with respect to this ambient manifold. And we have this. So if we put this in here, again, we're in vacuum. So then we are automatically satisfying this equation. If we look at this one, that's not there, that's not there. So we're just simply solving r equal to 0 or r equal to 16 pi e. The beauty of that is that if you choose this value, this p value correctly, then you can prove that putting these in the Ricci scalar will give you an equation that is an elliptic equation. Remember, we discussed quite a bit in the context of the hyperbolic problem that we needed to have an operator that was sensible so that you can argue and show rigorously, if you care, that the problem is well posed. Well, the same concept of well posedness applies to elliptic equations as well. There, you're not evolving. What you want is to guarantee that you can give, say, asymptotic boundary conditions, if you need maybe boundary conditions in some holes that you may have inside or not, that will make the solution to that problem robust in the sense of you change the boundary condition ever so slightly, you get a solution that is quite close to the problem at hand. So this is something like Jimmy York a long time ago indicated that if you do that, then the equation of motion is fine. I mean, the equation, though, you can solve that equation and the problem is well posed. Now, suppose you want to use these to even solve the problem of a single black hole. So you can do that. You can show that the solution in the non-rotating case will correspond to Schwarzschild solution. But if you want now rotation, you could put boundary conditions that will say asymptotically the space-time has some angular momentum. But then you can show that there is no way to write the curved black hole solution that we know in this way. So physically, what it means is you have a slice, the initial hypersurface with a black hole sitting in the middle, let's say. The asymptotic measurement of the angular momentum is whatever you choose to give, given the boundary conditions. But then that is made, but then you're forcing this, you're forcing the space-time to be conformally flat. And since Kerr cannot be written in conformally flat form, what you have is a black hole, a rotation in the black hole, but it also has some gravitational waves, all kind of throughout the initial hypersurface, that will propagate and will be registered, they say, by an asymptotic observer as waves. So this is something that it's an issue. So the initial data, this has to do with what I said before. Even though you can formulate the problem correctly, you will not have 100% control on the physics you would like to have the problem do for you. There are other options. You can say, well, let's pull the same trick. I could do gamma ij, phi to the p, and here I can put Kerr. And same thing, I can choose kij equals 0. So nothing, you can say, well, nothing stops me from doing this. After all, you would expect that you put this here in the ansatz, this equation will be satisfied, and this one will give me an equation for phi that I should be able to find with the right boundary conditions that phi equal 1 is a solution. The problem of that is if you do this, you have an equation that is no longer the problem will no longer be well posed. What does it violate? It violates uniqueness. So you can find yourself that you look this problem, you put the asymptotic boundaries. Of course, now you're not going to have waves in here. But you change ever so slightly the boundary condition, and now the solution is very different. And this is something that was seen back in the year 2000. So there is that danger. So now, what is it that you'd like to do if you want to make contact with that? Part of the problem is, now let's go deeper in what the problems are. So suppose you're coming from early on with your favorite perturbative approach to construct the inspiral. At some point, you want to say, well, from here on, I'm going to hand it off. I'm going to play, because like you're running this relay, you're passing the baton to numerical relativity. You want to ensure that what you call mass and spin here for the individual black holes is the same of what you do here. That seems like a trivial thing. It's not an easy statement to make, because here, now the black holes are getting together, and we don't have a local notion of mass or a local notion of angular momentum. So something that you think you can do in the spiral regime begins to break down on here. And then, of course, the differences of any reasonable approach I would use are very small. But the smallness can affect the waveform, and you want to have a very as accurate a waveform as you can and do the whole thing together. So that's in general, rigorous terms, this is not solved today. And I don't think it can be solved. It's something that one would have to choose, or one chooses some practical solutions to this and then lives with the consequences. So this is one way of attacking this. There are other conformal thin sandwich. These are names. They all kind of share one way or another these issues that I mentioned here. So there is nothing wrong to setting two black holes in this way or solving the problem. But what you have is you have some amount of uncontrollable initial amount of gravitational radiation. So if you see papers where they show the gravitational wave purely done numerically, you're going to see a blip at the very beginning. And so much so that the blip is always there that it has a technical term, junk radiation. So as well. And then after the junk radiation, you wait a little bit, and then you have a clean waveform that you can try and match. And the other unfortunate consequence is that typically you will end up with some amount of eccentricity. So the black holes have some eccentricity. Of course, if that case is the one you're interested in, fine. But you would like to be able to specify the amount of eccentricity you would like your initial data to have. And so then in practical terms, what people do if they want to kind of set a quasi-circular case that has no eccentricity, they get the initial data in as good a form as they can. They evolve it for a little bit, a couple of orbits. They realize there is some eccentricity. They come back to the initial data, change the parameters ever so slightly, and they iterate till they find something that has acceptable levels of eccentricity. Of course, the problem is that is time consuming, and you're doing one per case. but this is the name of the game nowadays. Yes. So, yeah, so what you do, I mean, yeah, the computer will solve, but there is a non-uniqueness intrinsic to that. So then you change so you say, I want to put a little bit of, turns out that there are two ways. Like you have a solution that phi, one is a solution, and another one you have one where it's not one, it's slightly different from one in the interior, it becomes very close to one at your boundary conditions in a very rapid kind of decay. And you cannot control that 100% because the equation is not of the type. Here, there is something called the Yamabe type of the equation satisfying maximum principles. These are a bunch of words, but this is what people study, and then they show that. In an interesting kind of side comment, I was once at a panel where we were reviewing proposals, and there was someone in biophysics that were presenting, well, I have this equation. Look, I have which describes the membrane of a cell. And every now and then, it would do this. And it was amazing. This is an equation that explains how cells divide. But it was ill posed. So and the solution to this type of equations and the Yamabe type is something that mathematicians study today. So the point being, good, the initial data is a problem. There are solutions. They all have a little quirk. Now let me discuss something else. So now, okay, we're back here. Suppose you have constructed your initial data. Now you're trying to evolve. You'd like to know where the black holes are going, maybe for trying to understand what you're going to do inside. I mean, we know inside the black holes, there is a singularity. What are you going to do? If you try and evaluate something there, it's going to blow up in your face. So there are a couple of tricks you can play. One is called excision, so singularity excision. This goes back to some idea by Bill Unruh. Which says, okay, once you find where the black holes are, and remember, we don't know what the black holes are. We can never know what the black holes are because the black hole is a teleological quantity. It's that boundary of the space-time that if you live forever, you can never see inside. And so at any given slice, we don't know what the black hole is. There is another concept, which I'll discuss in a second, which is kind of a good stand-in for the black hole. But suppose you know where the black hole is, or a good proxy for it. Inside, you have a singularity. So what this approach says is, well, go sufficiently inside. And once you're inside enough, then you can cut it out from your domain. Is that clear? And so just to, every now and then, I'm going to jump to this side of the board and make connections with the hands-on problems you have. So one of the problems you have is think of box phi equal to 0 for, say, Schwarzschild. So assume that the background is given to you. If you choose Schwarzschild, the standard Schwarzschild coordinates, you know there is a singularity at r equal to m. That's a bad system to try and do this trick. You would like to have some coordinates or some slicing that goes through the black hole. So if we look at the Penrose diagram, you want slices that somehow go inside the black hole so that you find out where the black hole is, and then you say, I'm going to cut it here. So why do you have the right to cut it here? Well, it goes back to what we were discussing yesterday. So if you write this, remember we had the field phi f, comma t. Now you have a matrix phi f, comma r, let's say, if we're in spherical symmetry. And then first thing, the matrix has the right properties. We have a full set of eigenvectors, all good. We can ignore the right-hand side as far as the characteristics is concerned. And we can look at what the characteristics are. And we can see that far out, if we use a good set of coordinates, an example is pi negative Goodstrand. I think that's a suggestion I have there. Outside, the eigenvalues are 0. And if you're far enough, it's plus minus 1. You expected that. I mean, at very far distances, the metric of the black hole spacetime arbitrarily closely gets to flat spacetime. So this is what you expect. There's a mode that goes to the right, a mode that goes to the left. And because we introduce a definition of pi as phi comma t, there is one that is 0. But what happens is as you get to the horizon and inside, then remember the plus goes to the left and the negative goes to the right. As you go cross, this begins to have a functional dependence with R. But as we cross the horizon, then we no longer have two signs that are different, positive and negative. Everything becomes positive. This one stays 0, but everything becomes positive. So everything is falling into the black hole. And the reason we were discussing this equation and say, well, I have chosen coordinates so that I have a positive number 1. It doesn't matter. The solution, the general solution to this equation is for the type some function of t plus x. So this is just a description of the solution in terms of characteristics. So what this says is that, say, take 2 times, so t equals 0, t equals 1. Whatever feature I might have at any given point, at any given time, then at a later time, this has to move to the left. To the left. So for this problem, if I ask how many boundary conditions can you give, just one, right? It's a first order differential equation. Where is that boundary condition? In the left, on the right? This tells you have to be here on the right. And here on the left, you give nothing. You just slant your, say, if you're doing this numerically, you slant your numerical algorithm, and the thing just goes in and disappears. From, if this is your computational domain, just falls off the cliff. So the very same thing happened if we chose reasonable gauges inside these regions. And so this is the approach that is called singularity excision, and you can go. And then there are, say, a large number of the community uses this approach. The very first binary black hole collision that France did exactly was using singularity excision. But then quickly thereafter, there was another approach that was also made a standard, which is called the puncture method, which I don't like the name, but let me describe what it is. Okay, there. You can take advantage of thinking that beyond the black hole, lots of things can happen. So in particular, you have the other quadrant of Schwarzschild, let's say in the case of Schwarzschild. And so these slides can come in here and end up in that Rn. And as long as you have a gauge that doesn't let you get too close to this singularity, you're going to be OK. And so this is what this R method is. It goes to the other sheet if you want. It delays things here so that it doesn't get close to the singularity. And how is it going to do it? It's going to tie the gauge, the advance of the lapse, to the extrinsic curvature in a way that the stronger the curvature is, the slower the time passing will be, and then things get slowed down here. But on this side, it just keeps going. You're solving this numerically, how do you teach the other side? No, it's a great question. The initial data already have that goes to the R sheet. And so then you just are controlling what happens in the R sheet. And the another dirty trick that is in. No, and that's OK. I was about to say that. Thank you. Thanks, Matthias. So it's not much more expensive because here, can I say this? You're beating the crap of the solution. There is a dissipation here that you're just, so it's not very refined here. And dissipation is just really taking care of this. It's another type of brute force approach. The excision, of course, is quite brute force, elegant in spirit. And this one does it in a different way, but same thing. And we're going to get back into this in a second. So how do you find where the objects are? You construct what is called an apparent horizon. Which just in very basic, I'm going to write what the equation is in a second, but in very basic terms, what it is you go to a surface. Now imagine this is not the event horizon. It's what this thing that we're going to call apparent horizon. And you imagine sitting on the edge of a surface with a flashlight, and you turn it on. And then you ask what happens with that null front. And if that null front stays there, it doesn't diverge, nor it converges, you're going to say this is a trapped surface. And in fact, if it converges, you're always going to call it trapped surface. If you're at the very boundary where it neither diverges nor converges, this is the outermost marginally trapped surface, and that's what you're going to call the apparent horizon. And if your space-time satisfies reasonable energy conditions, then you can prove that this is inside the event horizon. You can also prove that if to the future of some given time nothing else happens dynamically, then they will coincide. So for all intents and purposes, if you wait long enough, and where all the action has taken place, and you look for the apparent horizon, it's a very good proxy for what the event horizon is, even though you haven't evolved forever. So in mathematical terms, what does it mean to shine a light? Well, you say, first, I need to construct a null vector. Let's imagine it's like this. N was our unit normal to that hypersurface. So this is a vector that points that way. So now imagine I have the unit normal on that slice that points away from that surface. So I can now make a vector that points off the surface in the null direction simply by adding these two and normalizing. So we can say this has norm 1 or -1. We have a signature minus plus plus plus. So it's -1. This has norm 1. And if you check, the norm of this is 0. Then you can say compute the full divergence of that vector. That would be the expansion as seen from the full spacetime, but we want something that is intrinsic to the hypersurface. So let's slightly modify this. So this is the rate of change of that null vector, but let's hit it with this, with intrinsic curvature. And let's call it this. How am I going to call it? KAB. And then we're going to define the divergence of that vector as simply being the trace. No. So this, sorry, I mess up all the indices. Thank you. And as I said, if this guy is less than 0, you're going to call the surface trapped. And if it is equal to 0, it's the marginally trapped. And the outermost one is what we're going to call the apparent horizon. And this can be understood at every single slice. Have to be careful. Let's call it here. Suppose you have a star that is collapsing on its own, and it's going to form a black hole. This object, or the surface that we identify by looking for this, need not be smooth. They can be jumpy. I mean, they're very jumpy. So imagine a collapse situation. This is a star. We have r equals 0 here. Let's say, well, this is the origin. And this time. And if we ask, when does the event horizon form? Well, in some sense, the event horizon knows from way, way in the past where it's going to be. So it's that ray that essentially was coming out in here, that null ray, and then decided to become asymptotic that way. So this is the boundary, this is the null ray of the event horizon. But the apparent horizon need not exist. In here, the event horizon already exists. It's this null ray. The apparent horizon need not exist until there is sufficient focusing power in our curves slice that it might kind of show up here. And it might have this kind of size. It starts here. And then it rush out because it's space-like surface, and eventually meets this one and goes away. Maybe it's further out. So this is the apparent horizon. And so when people do simulations of binary black holes, you have these two distinct surfaces, and all of a sudden the apparent horizon that join both of them pops up. Any questions? Okay, but we're still not even getting in the business of waveforms, and maybe that's what you want to calculate. So let's discuss that last piece, or maybe I can just erase this. So we were chatting with Jim Stone yesterday, and I mean, GR is to get the waveform is such an yes. Go ahead. Yes. Yes.
I don't know if it's just like your drawing, but it seems like all your slices go from like space-like infinity, and then is that like
yeah. So this I naught. Great. Thank you. Yes, indeed. They go all the way there. This is in the Penrose compactified diagram. So if I have a surface that is time-like, purely time-like, they have to all kind of end up there. If not, if it turns around and meets this one, but thinks this is kind of a perfect headway for what I'm going to say next, then the surface has turned into a null surface because it's meeting it's meeting Scry. But yeah, so we're chatting with Jim. Like in some sense, the construction of the waveform is tremendously inefficient. You're solving for the full space-time, and then you're getting this observable somewhere that is just dependent on time and two dimensions, the angular dimensions. So you work really hard to obtain that thing over there. What's that thing and where is over there? So it is gravitational waves. It's this concept that if you kind of open, I don't know, the big book, I think someone called it the other way, the big book. It's just such a horrible description. Like you have this geometrical theory, and then you said, assume you go sufficiently far, assume you pick the right set of coordinates, assume the space-time is sufficiently close to flat, and if you're doing it there, then the Einstein equations can be rendered into something that says box of H being the strain or the gravitational wave, and it has these properties. There is a rigorous way of obtaining this, which is due to kind of Penrose, which says you take the space-time, go all the way to infinity, add a cap to your space-time. So imagine it's embedded in the larger space-time. This is what's called Scry. And then you can imagine this null ray that is tangent, and you can also do it with the orthogonal one. Either one is fine. And you're going to ask, say, what do geodesics do here when a perturbation gets there? The only thing that can get to infinity are gravitational waves or electromagnetic waves or scalar waves. Anything that is massless can get to infinity, nothing else. And if two observers feel this kind of geodesic acceleration between the two of them, then this is a wave. And this can be obtained completely in geometrical terms. And then you can see that it agrees with the standard definition that was kind of more pedestrian or more practical in nature. But then you can only understand that at infinity because one thing you can prove is this surface is null. So any little departure of that surface is produced by a wave. So it's not, sorry, it's null and flat. And so the departure, the waveform is sitting at the one of our expansion of that. And if you choose the right gauge, then this you can obtain from there the strain that kind of the gravitational wave detectors are getting. So how do you get there in the first place and do the computation if what you have is access only, perhaps to a portion of the space-time, and these slices, as you ask, are going here when what you want to measure is here. So here is where you can prove the space-time has some mass. That mass is decreasing, and it's decreasing by the amount of stuff that is going out there in terms of gravitational waves, and then you obeys the so-called bonding mass formula, where you can say there is a mass that is varying in the following way. And this shear is the shear of that null vector that is tangent to the hypersurface, to the null surface. Okay, so now you can say, well, what is the thing that I can compute that will have this for us from the point of view of things that I can calculate in space-time? And this, of course, is part of the definition that Penrose and Newman gave. There's a Biel scalar. There's a Biel scalar. This is the same Biel of here, right? That is constructed in this way. Okay, so let me explain what I have in here, and then we'll make a cleaner connection. So N is the normal. So this is, look, I'm going to use N for this one and L for this one, actually going in the opposite direction. So imagine you are at a given time. This, imagine it's a null surface. So the gravitational waves propagate at the speed of light. So anything along a null surface that is outgoing is just simply kind of a constant here. Asymptotically, the phase very much like what we had here. If you're very far out, you have something that is behaving this way, t plus minus r. And when you go sufficiently far, the only thing that gets out there is the piece of, say, if you have this, I have that solution and this other solution. So only this piece makes it all the way to infinity. Yes. And so then if you're a dot cut, I'll tell you why I made that comment in just a second. Then you can obtain by thinking of this N, these are things that are projecting your Biel along kind of the orthogonal direction to this null surface. This M bar and M, the M bar is a vector or a null vector that is tangent to the cut. So this cut is a sphere. So a vector tangent to the sphere, this is what these guys are. And this is, again, if you choose the right gauge, this is the following. This will give you the real part, gives you the second time derivative of your strain in the plus polarization, and the other one is the cross polarization. One beautiful thing of this, remember I said if you go sufficiently far, then this is just a constant. At that hypersurface is a constant. So what you can do in practice is compactify the space-time. So let me just tell you why I'm talking about that. Suppose you might as well just think of here. You have that slice. You can ask, well, if I want to extract the gravitational waves, I want to go as far as possible in my numerical scheme and measure things there. If you want to, one option you could do is let's compactify. We take infinity and bring it to a finite distance, right? So that we know how to do the transformation. But if I have a feature here, and these are my kind of grid points, and this is say infinity, and these are my grid points, the physical distance between these 2 points is something, but the physical distance between these 2 points is huge, right? So something that will look like a smooth function in the inner part of your grid will be extremely high frequency in the outer part of your grid. So this is going to be absolutely horribly tracked by your numerical code. So even though you could choose to have the boundary further out or as far out as you can, here you're going to be doing an awful job at describing the solution. And so people in the community use this trick to compactify, go all the way to infinity, I naught over there, space like infinity. But what they have in practice is dissipation, numerical dissipation that beats everything off here and makes it disappear. That is if you're choosing space like hypersurfaces. But if you go in this direction, you're writing the wave. You're writing a constant phase as you're in each null hypersurface. So this one you can compactify. Doesn't matter. You don't have a feature that has a strong varying personality here. It's just a constant. And so then you can compactify and go comfortably all the way to infinity. Yes? Say again? You use, for instance, I can say I have a coordinate r, right? And I'm going to map that coordinate into a coordinate that goes like x equal r over 1 plus r, or something like that, right? So this is at r equals 0, this is 0, and at r equal infinity, this is 1. So I took my infinity and then put it here, but the price I paid is that here I have reasonable resolution, there I have awful resolution, I have to live with the consequences if I do that. But if I use characteristics, then I'm fine. So this is to say that initially, so most codes nowadays, because of historical reasons and complications of adding everything else, but we're moving beyond that now, or some groups are going beyond that. They were saying, okay, the gravitational waves you're going to compute by obtaining the psi4, computing the BIL, constructing these things at a local kind of world tube, let's say here. And then, so you're extracting at a finite distance, but then you take this surface, say that surface, correcting for the fact that you have to compute the retarded time, and then make sure you have something that is converging to that's something you will have at infinity. Is that clear? Nowadays, there are applications of something that's called Cauchy characteristic matching, Sigma using the SXS coloration, spectral coloration, or the spec coloration. Sorry, I don't know the name. It's doing precisely, you have space-like hypersurface, match at some boundary with null hypersurfaces, go all the way to infinity and extract things there. So this is like 30 years in the making, but now this is available. And it's important for more than one way. Again, as I said, as time goes by, the bar, because of the detectors are getting better, and further detectors will come along the way, the bar is getting higher and higher what you have to do. So suppose you just computed psi4. Out of psi4, the real and imaginary part, you get this and that. Okay, but your observability is the strain, so you need to iterate it twice. But if you iterate it twice, you're going to pick a linear function that you don't have control on. So how do you fix it? What people did, and like it's still done today, is to force the strain to be such that asymptotically at late times, it goes to 0. And also at early times, it goes to 0. So that's that waveform over there. So let me just recover my waveform. Ouch. So you do this integral. And you force this to go like that. So how many of you have heard of memory? So you throw it away. So by fiat, we've been throwing away data. The community has been throwing away with there. It is complicated because if you have a short time frame where you're obtaining the gravitational wave, the memory is a very low frequency thing that starts at minus infinity all the way to plus infinity. But now there are clever ways to try and ensure that if you match within spiral in the right way and you take care of this annoying kind of not easy to determine mapping between the in spiral parameters and the merger parameters to really fix that error or that issue. And now the gravitational waves with waveforms are becoming available. So what people demanded was that this is true. So after you do the 2 iterations, this was 0, was going, or was, if you want, varying around 0. Yes, yeah, for both of them. Yeah. Oh. Yes. This, which one, sorry? These are null, yes. So say again, I didn't hear.
Are there any like extra details here with them being null hypersurfaces? I remember a lot of the smaller metrics that you do on like the 3 surfaces, they usually have like some asterisk if you're doing a lot of null hypersurfaces.
Asterisks?
Details.
Oh, detail. So what happens with the characteristics, I mean, in some sense, they are the ultimate kind of end of the spectra with respect to what we discussed yesterday with respect to writing the Einstein equations. When we wrote Einstein equation with respect to spacelike hypersurfaces, we implicitly were asking the full freedom of coordinates to be at our disposal. And I'll discuss a little bit about how do you do that. In the characteristic case, you give it all up. You say, I don't want that freedom anymore. There is a small residual freedom that you have, but you are insisting these surfaces to be null. So as a result, as opposed to say iterating 12 quantities, the metric, the intrinsic metric and the extrinsic curvature through first order differential equations, or 6 quantities through second order partial differential equations, here you only iterate in time 2. Everything else is constrained. So if you know the value somewhere, then there are radial iterations on the null surface that are imposing the fact that this null surface is a null surface, that you follow that wavefront. So that's beautiful when it works fine, but you have the possibility of caustics. And when caustics takes place, then you have a coordinate singularity. So coordinate singularities are kind of unavoidable. And then, of course, you could always go, like in this case, sufficiently far out that the caustics would have happened in here, and so then you're safe. But if you want to do the full problem of characteristics, then it's going to be a nightmare. Of course, that doesn't mean that the coordinates are going singular. The spacetime is perfectly regular. So you could invent all sort of things to address that. And we're chatting with Tim about options, but they're yet to be implemented. But historically, if there is a problem that can be tracked with the characteristics versus everything else, the characteristics is much simpler, much more robust, and cleaner. And this is why it's ironic that if you ask most people in the camp of numerical relativity, say for astrophysical purposes, how do you do numerical relativity? Most of them will say you have to use a Cauchy slicing. And in fact, some would say the only way to do numerical relativity is through a Cauchy approach. Well, if you ask that to people doing holography, they may answer exactly the opposite. It's the only way to do characteristics because 90% of the applications on that camp use the characteristics approach. Okay. I really don't know why I erased there, but. All right, so now let's just, yeah.
It's not a particularly important point, but people always show the memory as like at the end of the waveform, it ends up at a higher level, right? But of course, you can define that as 0. I mean, what's actually, are you still setting the constant in that second integration to 0 for the numerical bit, and then after the.
You're right. I mean,
sort of
right, the memory is a net change from beginning to end. And that you can do this, and it's the same. So that's a choice. And so the choice that is being made is asymptotically in the past, it was 0. You could imagine that's where you set your ring of test particles, and then you wait to the future, and then you see where did it go. Okay, so just in general, oh, no, wait, I had another thing. Yeah, just a word, very quick about gauge conditions. So and so here I'm going to say something, but I don't want to say a lot because I don't want to give the impression that there is a particular set of coordinates that you should use. There is a particular set of coordinates that have proven useful in the context of binary black holes, of the cases that people are studying, but they need not be the only ones, nor they need to be useful for other applications. So be warned. So, but in the context, say, of the Z4 or the BSSN applications, in the context of going back to Matthias' questions of trying to implement this type of approach, not the excision, then something that you could use, for instance, you could demand, and let me kind of pictorially just give the main features of these. So imagine you have a time derivative of your alpha. This is the lapse, remember that thing that was measuring the proper time at any given point if you went normal to the hypersurface. You can say this, I'm going to choose it to be proportional to alpha squared. I'm going to write it this way because this is a standard way of people writing it. So the key thing is that here you're tying the rate of change of your lapse to the trace of the extrinsic curvature. So it really wants to tell you how much the extrinsic metric, how much is it bending as maybe curvature is getting larger. And so then if you choose like f of alpha, the function, to be 0, then you're saying alpha is a constant, and this is what we call geodesic slicing or lapse equal constant. If you choose to be f of alpha to be equal 1, this is the harmonic case. Remember, harmonic was, okay, you choose box of x mu a to be 0, so this is t, x, y, z. If you spell out what it is, and you ask, what does it give you for the alpha? What does that imply with it for the alpha? It's essentially dt of alpha, alpha squared k. And you can play exactly the same trick to find out what is the shift condition that will give you the harmonic relation. But what people are using mostly in that approach, oops. This is called the 1 plus log. This is related to just having the rate of change of alpha tied linearly on alpha and the extrinsic curvature. For the shift condition, a good option has been, and I'll write it first, and then we're going to make a comment. Hopefully you remember I made a comment in passing. It's going to be a second order relation for the shift. This is a new function or new vector that we're introducing. Just so that to write this relation in first order form. So the key thing is that notice that you're asking the change in the shift to be tied to the change on these extra variables, the trace of the Christoffel symbol. So you're tying very much the coordinate conditions to the behavior of your field. So this is just to exemplify that the equations of motion, and people, you would hear this statement: the ADM equations lead to a nilpotent or problem for Einstein equations, and that's not really true. A convoluted choice of alpha and shift, even for ADM, can lead to a well-posed problem. And in particular, this message here is saying, notice that the rate of change of the lapse and the rate of change of shift are tied to the dynamics of your fields, the extrinsic curvature here and the Christoffel here. So this is related to the comment that we were making before. We work very hard to leave the freedom in the coordinate choices there at our disposal. And the kind of things that work today is that it's not so much free. that somehow we're tying them in a judicial way to the dynamics of this problem again, to the dynamics of our unknowns. And it's not too dissimilar to the comment we made in the characteristic case. We give out all the freedom. The freedom is such that the dynamics is saying this is the gauge I have to use. So this is just, it's interesting to see that there is kind of this is coming up in a different way, but the very same observation here. But as I said, I wanted to stress these are not the only choices. But just be prepared to experiment a little bit and know what you want to do. In particular here, that choice is the one that makes the evolution here kind of be delayed as it gets close to the singularity and not run into it and then have the coordinate misbehaving. Okay, so now let's change a little bit of the subject. I want to kind of come out of the gravitational wave to perhaps then come back in. And I stress some things that a priori one might not have thought, but I think some of the most interesting applications nowadays are in this camp. So beyond, of course, I have two black holes that are coming together. It will produce a waveform. And of course, there is a huge impact in helping the data analysis enterprise. Numerical relativity is much more interesting than that. And then what do you want to do? So particularly, you might want to be interested in using numerical relativity for astrophysics. Of course, knowing the black holes and the population is astrophysics, but I'm saying more richer than that in the context of what I say, multi-messenger astronomy. So here you're saying, well, I don't have black holes, or if I have black holes, they're interacting with something, matter. I'm going to heat the matter up, either because there's an accretion disk, or you're smashing two neutron stars together, and what you're going to learn is something about the property of the matter itself. In particular, the spiral becomes complicated. And the spiral of black holes is simple because two things happen. When you look at the black holes themselves, they do two things really badly. One is to absorb energy, and the other one is to feel tidal effects, something called the tidal love number. Like tides are produced by the effect of the moon on our oceans. So a black hole doesn't care that much about that. The tidal proportionality constant is 0, but neutron stars do not have that property. So towards the end of the spiral, you end up getting some modulations due to these effects actually playing a role. And it can be computed in the early spiral, and you have some values in isolation, or if they are sufficiently far. As they get closer and closer, the perturbation approach no longer captures what it is. And then you have a significant kind of modulation. Then these two stars smash against each other, and all hell breaks loose. Yes?
The probability of a black hole is 0. So well, there should be some work on that when you get leading order.
Yeah.
So you see this deformation?
No, because there are two things that are playing against you there. I mean, in numerically, you would see them, but then would it have an impact on the gravitational waves? No, because this is just extremely low. The compaction is, well, there are two things that help you in the case of neutron stars. They're fat, and they have a tidal deformability coefficient that is largish. And black holes are very small, and they are themselves very compact. So, and of course, in the merger itself, then a lot of things happen. And when you go into astrophysics and multi-messenger astronomy, not only you have to deal with the equation of state of the object, but also other physical effects, like neutrino productions might completely affect what the post-merger dynamics is. Magnetic fields might also have something interesting to say. And then, okay, the question is to target this is when you get very dirty in the astrophysics, and that's a very tall order, and lots of great people are working on that. The requirements for resolution, computational costs begin to shoot up. Luckily, fortunately, there are really advanced codes that are enabling this work in a very strong way. You could also be interesting perhaps in testing generativity, and maybe we'll discuss more tomorrow. Yes.
So people usually model sources of perfect.
As what?
Perfect fluids.
Yes, and
Like have people figure out how to model superfluid?
no, but there are people like I know Neil Sanderson has been looking into that. There are people that are trying to, and myself was included in some of these works, to phase transitions and things like that. But we're beginning to scratch that picture. That problem then becomes, are you interested in it or not? Like when the merger takes place, prior to the merger, these things are not playing a significant role. Neutrinos are not saying anything. Magnetic fields are weak and not affecting the dynamics in any way, shape, or form. The merger happens, and then those things are significant, or could be significant, depending on whether neutron stars decide to collapse to a black hole right away, or whether it wants to linger for a while. If it wants to linger for a while, all these effects will rule the day. But that's where the detectors that we have today stop seeing. And okay, the gravitational waves detectors stop seeing, but the electromagnetic telescopes continue seeing. And in fact, a lot of, like the GW170817 is a waveform from, if there hadn't been a flash, the waveform was completely consistent with binary black holes. It was because of the flash that you actually see that. And now by analyzing the structure of the light curves and multiple frequency bands, then you begin to build the case for what happened after the gravitational wave detectors have nothing else to say. And that's a very interesting thing, but I said it's very kind of complex astrophysics that need to be completely figured out, and people are working hard at this. You can try and test GR, that may be the question that drives you. We'll talk about this perhaps tomorrow. And I'm going to throw this in and I'll show you some examples. You might be interested in dark matter, or maybe even dark energy. Okay, this might tie with this and the same thing with that. But I'll give you a very precise example of this one, something very exciting. And you can also try and test. If you're going to test GR, you may also want to test the black hole part, the compact object paradigm. Is it true that the compact objects that we should be worrying about is just black holes or neutron stars? Or is there something else? And numerical relativity has people working on all these fronts. So let me just give you a few examples. And it also ties to perhaps some of the assignments. So one thing we tend to think that we know is that black holes are stable. But are they? And then they're not. Like we know that if you perturb black holes with massless perturbations, yes, they seem to be stable, perfectly stable. We actually smash black holes together. They seem to be just perfectly fine. Even more interesting than that is that as the black holes are trying to merge, if they were to merge earlier, there is way too much angular momentum. You would form a naked singularity, ultra Kerr. But no, the space-time says, wait a minute, you need to calm down, radiate a bit more angular momentum, and then form the black hole. And then the final object is a black hole that has some given spin. An interesting, perhaps, thought is when you look at the GW150914, or the very first, say, simulation of black holes that are colliding, if you have two objects that have equal mass, no spin, they merge. If you ask, if the system had tried to maximize the entropy change, what would have been the final black hole parameters? It would have been a black hole with about twice the mass and zero spin. Yet the merger doesn't produce that. It produces twice the mass and about a spin of 0.7. That doesn't maximize the entropy, it's just one in between. So why? But the interesting point, or the point I wanted to make here, is that the moment you introduce interactions of the black hole that might be spinning with massive fields, things can get very interesting. In particular, you have this phenomenon of superradiance. You can take energy away from the black hole and put it into something else. And here is where you could say, well, I know that massive fields can extract energy from the black hole. So you might want to say, oh, I want to study a black hole interacting with this massive bosonic field. And why? Well, because there are models for potential dark matter descriptions that involve massive fields. An action field is one of them. And you can try and do and say something about that if the right behavior takes place. But then you can try and be smarter than that. One thing you could do is just, I think Neil was saying this also as well, before you do a computation, think a little bit. Is that the problem you need to solve, or could you solve a different problem that will tell you the same answer that you're trying to seek? So here, we list, and Franz Pretorius and Neil Simonsen have been looking at massive fields that are not scalar, but are vector. And the reason for that is that if you study the instability, so people have recognized by doing linearized perturbations of black holes that have spins that interact with massive fields, that this superradiance effect can take off, but a bosonic massive field takes off at a kind of a slow rate. The vector field takes much faster. But the details of the dynamics in and of themselves, the quality of the details are the same for both. So what they did is took a black hole interacting with a massive field, massive boson field, a vector field, and then just ask the question, what happens when the system evolves and saturates? Because the linear approximation can only take you so far. You can understand there is an unstable mode that will take off, but that will give energy to the field will grow, but how much is it going to grow? How much energy is going to take off the angular momentum? How much mass of the angular momentum? And they have this very cute application where you can see that, what was it, about 40% of the angular momentum can go into the field. 10% of the mass can go into the field. So what you have in the end is a black hole that was here and have all this stuff around. And this you can also study, we had studied earlier, in a different setting, a setting where it was an anti-de Sitter. It was gravity, and for a charged black hole, not even a black hole that was spinning. But that was a problem that you could do in much simpler ways, in spherical symmetry, and then also see that indeed this superradiance is such that takes this energy and angular momentum out of the black hole and put it some distance away. But now this in itself, in and of itself, is unstable. It begins to decay in longish time frames, but it decays and it has a frequency of decays that is very tied to the mass of this scatter of these massive fields. And so as of now, LIGO, Virgo, Kaga, have this great opportunity, and they are doing it, and maybe a paper will come out in not too long, where they say, well, if you actually form this and this is unstable, it will try to kind of decay and will generate a quasi-monochromatic signal of gravitational waves that slowly decays with time. And these are details that you could only get through numerical simulations. And so the beautiful thing is that the detectors, not only after they see one of these events, now you know where it is, you know when it happened, you know the time scale of instability because the numerical simulation told you how long it will take. So the time scales are, the dynamical time scales of that problem are in the order of milliseconds. So you can argue that in the order of a few hours, the saturation of this event would have taken place. And in the order of a few days, you're going to have this quasi-monochromatic waveform that you can go target and put some bounds on. So it's a way to say there's gravitational waves, but what you're after is one of these models. How much you believe the models, okay, that's a different story, but it's something you could do. I think, is it double time? Yeah, okay, so then I'll stop here. I was going to mention in the context of that, there's very interesting work that Neil Simonsen and Willis and others have done, and Katie Clough and Pau Figueras on boson star and Tamara Efstafeya, where you actually create these objects that are compact, that can mimic black holes, and then you can ask to what degree is that waveform degenerate to the waveform that you think you would have, or you know you have for binary black holes of the same parameters. And okay, there is an interesting story. I'll tell you a little bit tomorrow, but I'll stop here. Thank you.